Hello and welcome back to another video with It's Dr. Dan, and today we're going to be learning about nuclear chemistry, radiation, and its applications. So what we're going to be diving into is what is radioactive decay, what do we mean by a nuclear reaction versus a chemical reaction, and we're going to be looking at essentially the ionizing power and the penetrating power of the different types of radiation and some of the applications that this has to do in the world around us and in the health science field. Now, when we're talking about radiation, this is something that's not brand new. It's been around for a very long time. When it first started to come around, it was right after the advent of the periodic table, right in those 1860s is when scientists started to explore new possibilities of what are the atoms truly made out of. Now, from that, they started to realize that, well, the atom is contains of protons, neutrons, and electrons. What are they exactly capable of? Well, one of the first discoveries about these was is that there were X-rays being given off by different elements, and they weren't entirely sure exactly what they were until Wilhelm Röntgen discovered some of the basic properties of X-rays by essentially he took an X-ray of his wife's hand back in the 1890s. And for something that is over 130 years old, it actually has very good resolution. You can see the bones, you can see the rings on her hand. Even if you zoom in, you can even see her bracelet with her keys on in this X-ray is able to resolve all those little details. Now, once that was really seen, what that showed is that with this technology, that X-rays, which is a form of radiation, has a penetrating power. Now, but for some reason, your bones all of a sudden don't allow that those X-rays to go through. It goes through skin, but not bones. Why? What exactly does it all have to do with? Now, from there in the 1890s, several scientists, mainly with Marie Curie, her husband Pierre Curie, and another famous scientist named is Becquerel, discovered all these different properties behind radiation. Now, originally, Marie Curie was first awarded the Nobel Prize in 1903 by the physics community for her discovery with radiation splitting with those other two scientists. But she is one of the first people, first woman to have two Nobel prizes, one for physics, one for chemistry. And her one for chemistry was discovering the elements radium and polonium, which were also radioactive species. So with this, she was the first one to coin that term radioactive, meaning that there are these species that seem to give this signature or that something that can be that's being given off. It's an invisible light source that we cannot see with our own hands due to this unstable nature of these nuclei. And from there, people believed that this was this new cool thing that they could do all kinds of really cool effects from it, right? They glowed in the dark, they did all these cool things until they started to realize that there's a lot of hazards behind radiation, which we're going to be talking about and looking into in this video. So let's dive in and let's try to take a look at a little bit more about this. So the first thing is, what is radioactive decay? So the first idea here is that whenever you have a radioactive isotope, that is an element with an unstable nucleus. Now, when we say that's unstable, what it's going to want to do is that they spontaneously will decay, meaning it'll just happen, and it's going to decay into smaller nuclei. And when that happens, when it breaks down, it's going to emit radiation as essentially its way to release itself. How can it try to bring itself to a more stable state? That's the goal of all even chemical reactions and nuclear reactions is stability, right? That's even our goal as humans. We want to be stable. So whenever this happens, a nuclide that is, when I say a nuclide, this is referring to a nucleus of a specific atom. All nuclides, generally for these that are radioactive, usually it's 84 or more protons are always considered to be radioactive. So if you look at your periodic table, anything that's 84 and below, they are radioactive species. They are very uncommon elements, but they are the ones that tend to be that what we see, like uranium, polonium, plutonium, or radium. All these types of elements are considered to be very radioactive and very dangerous. So why exactly do they decay? Well, what is this all about? Well, the whole idea here is that nuclei that are unstable, it's extremely difficult for it to be able to maintain itself. So when we have a very big nucleus that has all these neutrons, all these protons. One way to kind of think about it is it's sort of like trying to juggle a bunch of things in your arms, right? If I have my hands full with, like, let's say a bunch of, let's say, fruit or apples or something, and I have like 4 or 5 in my arms, that's not too hard to cradle. But if all of a sudden I have 50 to 60 apples and I don't have a basket to hold them, they're going to start kind of tumbling out and start being really hard to maintain. Well, that's kind of what's happening. It gets really hard for the nucleus to hold all of this together. So one thing is that we actually can currently see is that small nuclei generally have a 1-to-1 ratio between their neutrons and their protons. And then larger nuclei start to crouch towards this 1.5 neutrons for every 1 proton, where essentially we can actually plot this and we can see this with what is known as the band of stability. So one thing is that we have this 1-to-1 ratio, which is this red line right down here down the middle. So this is where it's 1 neutron to 1 proton. And all the way at the bottom, these are like your beginning elements. So things that you can kind of think of, like, let's say if we have helium, for example, right? Helium has 2 neutrons, two protons. So it's 4-2 helium. Something like lithium is 6-3 Li. Carbon is 12-6, right? So it's all are 6 neutrons, 6 protons, 3 protons, 3 neutrons. There's a 1-to-1 ratio at the very beginning. But then all of a sudden, that band of stability starts to kind of venture farther and farther away from that point. Now, if things kind of wander outside of this stable region of this ratio that exists, that's when we start getting these different decay patterns where they're going to fall apart. So if something is a little bit lower than this region, you'll see that it'll do positron emission. If it goes above, it's beta decay. It all depends, does the element kind of exist there? Now, this isn't something you have to calculate, but it's something that to be aware of, right? If it goes a little bit outside the norms, it's considered to be unstable. So let's take a look at the different reaction types. So the first thing is realizing what is the difference between a chemical reaction and a nuclear one. Well, the whole idea here is when we've been learning all about chemistry throughout all the different chapters, chemical reactions all involve the rearrangement of the electrons, meaning that electrons are being exchanged between species, right? You see that their atoms are gaining electrons or losing electrons or sharing them. It's all about how the different atoms will be connecting to one another via this how these electrons are being transferred or shared. Now, the thing about it, though, is that there's no change to the nuclei of these different species, meaning that we never touched the number of protons, the number of neutrons. That never changes. The only thing that changed was electrons. So the big thing there is that the element identity remains the same. Even if a reaction happens, let's say if I have oxygen in a reaction and it turns into a product, there's still going to be oxygen atoms on the left. There's still going to be oxygen atoms on the right. They're still going to have the same atomic mass, same atomic number. That is always the same. It's never going to change. Whereas if I have a nuclear reaction, well, that's when there's actually a change in the nuclei, in the actual inner core of this atom. It's going to be having the protons could change, the neutrons can change. Something is changing in the core of this species. So because of that, there's a good chance that the identity of the element can change as a result. So meaning maybe the number of neutrons changes. If the protons change, it's going to become something different. And the thing is, we're interested in what new nuclei form. We don't really care about the charges in nuclear chemistry. So we don't really worry about the pluses and minuses. We're adding up what is the masses and the number of protons. So when we look at these different nuclear equations, what they are is essentially we're adding the top, the left and the right, and making sure everything matches. So what you're always going to see is some kind of parent nucleide, and it's going to be decaying into a daughter nucleide and breaking apart. So when I said that the left and the right should match, well, what we're going to be checking is the atomic number and the atomic mass. So when we have our atomic mass, so on the left here, so we have, remember these were A and Z is how we would denote those. So they have to match on both sides. So if you see the mass is 238, That means that the total of the mass on the right-hand side also has to be 238, right? If you take 234 plus 4, it also equals 238, so it matches. Same thing with the atomic numbers, right? If you look on the right-hand side, it's 90 plus 2, that's 92 total. It matches the atomic number on the left. So all these particles, they can't just vanish on us, but it did change the identity of this species. It decayed, therefore it lost protons, and you can see that, oh, because it's now a number of 90, it's going to be something new. Let's look at the different types of radiation and try to make sure we understand all the different types. So in my previous video, there were 4 major types of nuclear equations, and if you want to learn how to balance nuclear equations, I would recommend watching that video first. So when it comes to the 4 different types, the first one is alpha decay. So whenever we have alpha decay, the whole idea here is that the nuclei is losing 2 neutrons and then 2 protons alongside of it. So when it loses the 2 neutrons, 2 protons, the way that we can actually illustrate that is by, it's the same thing as a helium atom, right? If you remember the mass of helium, it has 2 protons, right? Which we can see from the 2 that's down below here. And when you add those 2 protons to the 2 neutrons, this is where we will get a 4 for its atomic number. For its atomic mass. Now, with that, when we are trying to look at these reactions, you can still see that everything equals up. So when we do 4 plus 218 equals 222, and then 2 plus 86 is equal to 88. Alpha decay is losing 2 neutrons, 2 protons. So we can show that with a helium atom. Now on to our next one. Beta emission is when a neutron is converted to a proton, meaning that when that happens, an electron or beta particle is released. So this is a very, very high energy electron. So when this happens, what you're going to be seeing, so I have a neutron on the left-hand side written as a dark blue, and it's converting to a proton, which is shown in pink. So when this happens, the one thing you're going to notice is that the mass number stays the same, because the way that we show a beta particle is with a 0 and a -1. So this will be a beta particle. And then typically we write it as an electron. Another way to show this as well is writing 0 and -1 with a beta symbol as well. And the one thing that with this type of decay process, you'll see that the atomic mass still equals to 14 on the right-hand side. And then on the left, and you also see that the total of the atomic number is 6. So it matches the 2 sides. The mass number stays the same, the atomic number increases. So this is a beta decay. Now there's also the opposite form of beta decay, which is referring to instead of the beta particle coming off as a product, sometimes you can also have where an electron can be absorbed by the nucleus. So if that is to happen where an electron is captured by the nucleus, because you got to kind of think that electrons, they are attracted to the nucleus. They're always trying to get in contact with it. So what happens if it does happen? If that occurs in an unstable atom, a proton is in that case going to be converted to a neutron. So it's going to be the opposite situation that's going to happen. So what we'll see is we'll see that that electron or that beta particle is going to be on the left-hand side instead, and you're still going to do the same math where we're adding up 14 plus 0, which I meant to write this as an 11 over here. And then you'll still see that the bottom is going to equal up to, so 6 plus -1 is going to be equal to 5 on the other side, right? So those 2 parts will still match. So it's just the 2 types. So it's in case you come across that vocabulary term of it being captured. So it's when the electron falls into the nuclei. Let's look into our next 2 types of radiation. So when we have positron emission, what we are going to be seeing here is when it's going to be when a proton sheds its positive charge to become a neutron. So it's very, very similar to electron capture. But instead, what you're going to be seeing is that when that proton is going to convert to a neutron, so I have a proton shown in pink here, it's converting to a neutron. And what the way that we are going to show that positron emission is with a 0 and a +1. And what you can see is if I add up the masses, it's still going to be a total of 11 on top. And then the bottom is going to be 5 plus 1. It's going to be a total of 6 on the bottom, which is equal to our products on the left. So when you have a positron emission, the mass number stays the same. The atomic number decreases by 1, okay? So this is one thing to kind of keep in mind too. Now, other things to keep and think through the thought process here is that your proton and neutron counts are changing too. So in this type of example, so being that if you look at carbon, right, we had 6 protons. Well, it's being converted to a total of 5 protons. So we have 5 protons and 6 neutrons. And on the left, you have 6 protons and 5 neutrons. So you can see that the proton and neutron counts are changing too. You can do this for any of them by keeping track of how many protons and neutrons are, which we'll be doing in our next practice problem video as well. Let's look at our last one. The last one is gamma emission. So what is gamma emission? All has to do with whenever you have a very unstable nuclei, where it needs to try to release energy. So gamma rays, what they are, it is a form of electromagnetic radiation in the form of light. So these are high energy photons that are being released and they are traveling at the speed of light. So whenever this happens, this can be used in very many practical applications because they travel very fast and they penetrate through almost everything. But as a result, being that they penetrate through a lot of things, they don't ionize everything in their path. So we'll talk about that too. So it's all going to be shown with zeros all around it, where it's just going to be releasing that energy as a result. Let's take a look at the next one. So when it comes to penetrating and ionizing ability, so penetrating all has to do with what the size of the particle is. The heavier it is, the harder it is to actually go through different things. The lighter it is, the more different surfaces it's going to completely just plow right through. So what I have here is I have a picture that has paper, skin, metal, water, concrete, and lead. So there's all the different types of different things that you could come in contact with radiation really easily. So if you were to say what's the heaviest particle, well, that would be an alpha particle because it had 2 neutrons, 2 protons. So something like that, well, it would hit a piece of paper and it would bounce off. The issue with that, though, is that when it hits that paper, it's going to ionize that surface very heavily because this is a very, very dangerous particle. Now, on top of that, well, whenever you have the penetrating ability, the lighter it gets, the more surfaces it can go through. So something like a beta particle can travel through human skin, but it would end up stopping via metal. So if you just had a metal surface or maybe the side of a building, it would easily stop to that. Neutrons are something that goes through a lot of different surfaces, which can be a little frightening, but generally whenever it comes to a neutron emitter, it's kept inside of water or there's some kind of water shield because water will just absorb that neutron to make deuterium. So now when we have something like gamma rays, gamma penetrates almost everything except for lead. So this is why a lot of different, when it comes to patients doing x-rays, they will have like a lead line vest. There's also usually whenever there's a gamma ray emitting, gamma rays are stronger in x-rays, keep that in mind. So whenever there is a gamma ray, it's usually kept in a lead container so that way it protects everybody around it. So now when it comes to penetrating ability, the ionization ability is the opposite. So if something travels a lot farther, it's going to actually have a lower ionization ability, and that's because of how fast these particles move. So gamma rays move at the speed of light, so that's why they can go through so many different things so quickly. Now, being that they are going through so fast, they're not going to ionize as many different species in its path. So if you come across gamma rays, it won't ionize like your DNA, your skin, everything that it comes in contact with as easily. It's something that you could essentially use for a longer period of time to maybe get rid of a cancer tumor or as a potential therapy. Now, alpha particles, on the other hand, being that when they can't penetrate anything, they are so heavy, they will come in contact with things for a lot longer. They'll have a longer dosage time. So as a result, they will end up ionizing everything they're coming in contact with. So if you end up ingesting an alpha particle by accident, so let's say if you're not careful with cleaning up after yourself, it can't come out of your skin. So it's something that will stay inside you for a very long period of time. So it's a little scary. Beta particles are usually right in the middle, so it's something that can be used to maybe damage something, but it also, or maybe even used as a contrasting agent because it can leave your body, but it still has some harmful effects behind it too. So let's look at an example when it comes to occupational safety, when it comes to the penetrating and ionizing ability. So one of the different stories of when it comes to radiation is that many different people have died due to exposure to radiation because the effects were not understood until probably until the 1930s and 1940s of what radiation was truly capable of doing. We knew that it was powerful, that it had a lot of applications, and it was this really exciting thing at the time period, but people did not entirely understand it completely. So when radiation was first started to determine that it was dangerous was around the early 1910s, where people started, because they were essentially putting it in everything at the time. When Marie Curie and all those other scientists discovered it, they were putting it into makeup, putting it into plates, cups, beauty products, you name it, because it had that glow in the dark quality to it. So a lot of people wanted to put it in things. Now, as a result, people were getting sick. It had a lot of problems, especially in Europe, where this really took off. Now, in the US, there wasn't really a lot of radioactive products available, except for there's one major case, which is a lot of it is called the Radium Girls. So if you ever there's actually a movie about it now. If and something that's even interesting to read about, it's actually a pretty sad story. Is that the factories during that time period hired a lot of women to paint watch faces with radium paint. Now, why would they use radium paint? Well, it was something that would be this glow in the dark watch where airplane pilots could easily see the hands on it because it'd be glowing. Now, the thing about this glow in the dark paint is that being it was made of radium, that is a radioactive chemical, which you can get very sick from. And this decay process that it undergoes is alpha decay, meaning that what the girls were doing is that they were told in order to get a very nice straight line on their thing to lick the edge of their paintbrush and then to dip in the chemicals to paint it and then keep licking the edge. So what was happening is they were getting it in their mouth and it would be ingested and it would lead to that exposure. So being that we're talking about alpha decay, as I was mentioning, it can't go through paper. So if you eat it, it can't really leave out of you. It's going to do a ton of damage. So as a result, a lot of these girls ended up getting bone cancer, where their jaws would fall off. They would get anemia, they would necrosis, meaning that their body is falling apart. If you really want to get into it, you can Google that and see some of the images behind that. It can be a little vivid as a warning. But it's something that really shows what this is capable of. So if you're someone who wants to work in radiation technology, you got to treat it very seriously because it can be something that can be very, very damaging. Has a huge application, but is very dangerous at the same time. So let's look at how we can detect it so we can protect ourselves from radiation. So there are a couple different ways to detect radiation to make sure that we are safe from it when we are handling it. The most common way is whenever you use a Geiger counter. So what exactly is a Geiger counter? It's essentially that device that you've seen on different TV shows, and it does that little tick, 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 tick sound whenever it's near a radiation source. Well, what it's essentially doing is that when you have radioactive rays, it causes the air to ionize. And what the Geiger counter is going to actually do, it's going to count all the different electrons that are being released from this ionization. So when the electrons are generated, essentially we'll be having argon gas that's going to be ionized by the radioactive rays, and we'll detect that from the radioactive material. So this is something that when they have any type of radiation leak or any type of, if there's like a nuclear device or anything that could be really problematic, you'll see the Geiger counters get brought out to make sure people are not being exposed to it. So that's one way. Another way is generally for anyone that works in radiation technology, if they're an X-ray technician or someone that actually might help with a lot of different radiation therapy and they are working around a lot of this. There's another way where if you have radioactive rays, they can expose a light protected photographic film. So when that happens, it's something that is like a little badge that generally these workers will wear on their chest, and it will change colors if you are around too much radiation. So it's like an early warning system rather than, because you don't know, you can't see it, right? So this is something that will change colors when you're near too much radiation. So a lot of people will wear it around like sensitive areas that could be more susceptible to radiation, whether it's like genitalia, or if you are someone who's pregnant, for example, then wearing it around like a baby to eventually be is a really good spot to put it to make sure, hey, everything is going to be okay. Sometimes you're also around radioactive sources. You might have mini Geiger counters near them in case there's a radiation leak. So it's something just that if you have a small exposure, it's normal, but you don't want a prolonged, chronic, long-term exposure is really the idea. And the whole reason for this is, well, when talk about radiation, we think like, oh, it's all these unstable things. It's only found in like the lab somewhere in like the middle of nowhere. No, a lot of this is natural radioactive species. It is all around you right now. You are exposed to radiation at all times, right? It's not always as alpha, beta, gamma decay, all this stuff. There are radiation is light, right? So you are exposed to light source all the time. They're not as strong as these other sources, but radiation's everywhere. So there are isotopes that are radioactive, right? So right now, like you have radioactive particles inside of you. So if you have like carbon 14, because you are made of mainly out of carbon, some of that carbon is carbon 14, which is radioactive, and it's always emitting different radioactive particles. A lot of soil samples that we have are there's something that you can detect radioactive particles. It's more or less in different areas, but that's possible. Food also, any type of food product, whether it's carbon or if you have like bananas, for example, they have potassium 40, which is a radioactive chemical. People being near anybody actually is radioactive. So if you're wondering what's that attraction between people, it's actually secretly the radiation between different people. Or just being in the open, right? So if you think of UV light coming from the sun, that is a form of radiation. But if it wasn't for your ozone layer, we'd kind of all be dead due to the cosmic rays from the interstellar space. So there is essentially the ozone layer is always protecting us because it absorbs most of the gamma rays that exist in space. This is also one of the reasons why astronauts need to wear spacesuits. It's not just for the lack of oxygen and how cold it is, it's also to protect them from cosmic radiation, which would even be worse. Um, One of the things about this is even though the ozone layer actually does this, if you fly a lot, you actually are going to be more susceptible to higher doses of radiation. Generally, pilots and flight attendants that are flying every single day, they will actually, it's confirmed that they always have a higher dosage of radiation. They're usually checked more often to make sure, hey, your levels are within a safe region within your occupation. So now what are the different types of applications behind this? Well, with this, there are all kinds of applications, but so some of them, one of the big ones is carbon dating or for fossils, artifacts, different rocks. The carbon 14 exists in all different species, living and non-living. And depending on how much of it there is, we can do calculations to figure out, well, what was the original half-lives of things, so you can figure out how much there should be in a given sample of when it was created. So carbon dating is really, really prevalent. Another one is when it comes to alternate fuel sources, being that we are trying to get away from the fossil fuel industry. One of the biggest ones is nuclear fission in the terms of a power plant, right? So if we split the atom, can it be used, because it generates so much energy, can it be used to try to power our cities and to try to keep all the lights on? Another example of nuclear fusion. So fission is splitting, fusion is all about combining together. So when we have that, that's how the sun essentially shows all of its light. And as a result, you have the different types of radiation that's being given off from it at all times. The atomic bomb, which being, if you've seen the movie Oppenheimer recently, is a form of nuclear fission. In terms of radiation as well, it's used to destroy human tissue, whether in a medical application, let's say if we want to get rid of a tumor, for example, or to get rid of a lesion, then it can destroy human tissue. But the thing is, though, it has two sides of that coin, right? You can use it for a good thing, but it also, you can get radiation poisoning, which is generally whenever someone has radiation treatment, they can get very sick. They can get very weak because radiation is flooding your body. It's very bad for you. For a very prolonged period of time, it can be very deadly. This is actually how Marie Curie did die from radiation poisoning. She only was, I think, probably around, I think, less than 50 years old by the time she passed away in the 1930s. So radiation poisoning slowly took her life. But the biggest application is really a lot of the imaging and medical treatment. So depending on where you end up using this, there's all kinds of different applications for where this has been used in our history over the past 120 years because it's one of the biggest ones. But being that many of you are interested in the medical industry, I thought let's focus on that and talk about some little cool examples of really where this is used, where we use radiation treatments to try to help and better people. Okay, so let's take a look. So when it comes to medical scanning and treatment, I picked two examples which are a little bit bigger to see. So the first one is whenever you have something known as gamma knife radiosurgery. So what this is actually takes gamma rays and focuses it in a very, very precise beam where it's like using a scalpel to remove a tumor. Now, instead of it being a traditional knife, it's going to be using radiation to do this. So what is actually happens here is when we're using imaging technology, we can shoot a gamma ray straight at the tumor, and this will, by irradiating and destroying this tumor, it will stop all cell growth. Now, keep in mind, this stops good growth of good cells and of bad cells. So that's where kind of the coin flip is, but it will destroy and try to stop any future cancer growth within that region. Now, the good news about this is something that's doable without needing to actually open a patient on an operating table. So it removes a lot of the general problems that it can arise, and it will slowly destroy the cells. So it's something that can be done over multiple treatments over a prolonged period of time by focusing and removing exactly where the tumors are. And so far it seems to be, based on studies, it has about the same success as a regular surgery, which is actually very promising. Now, another one, which is probably one of the most common that many of you will actually, if you do go into nursing or radiation technology, they're going to be sending patients to, is whenever you have a CAT scan. So if you hit your head real hard, usually you got to get your CAT scan or an MRI to see like, hey, is there any actual internal bleeding? Is there a concussion? Are there any problems? So the whole idea of what a CAT scan is essentially you have an X-ray machine that is going to be rotating around your body, and it's going to creating a 3D image of the area that's being scanned. Now, how does this all work? Well, it's X-rays that are going through, which form a radiation. So essentially different parts of the body will absorb it. Bones absorb X-rays, so you can generally get bone X-rays really well. But usually we end up using a chemical contrasting agent that will absorb that radiation. So that way it lights up on the scan. So for example, let's say if you want to see a brain scan, well, you can take 3D images of all the different layers to really be able to see, well, where exactly could there be a problem at, or maybe if everything's all healthy. This is one of the reasons why in anatomy you have to learn about all the different planes of the body and how you can try to view it, so that way you are able to interpret different data like this and know exactly what it is that needs to be referred to when we are trying to understand how we're looking at the body. Now, other areas where contrast agents are always required, this is usually where it's more soft tissue, so muscles, organs, anywhere that you can easily inject a contrasting agent or even ingest a contrasting agent. Maybe it might line something. So here we have like the intestinal tract, where it's really easy to try to, if you like engulf like a barium compound that's kind of like drinking chalk essentially, it will line your entire intestines, so you can actually, so the doctors can get an idea like, hey, is there a leak? Is there, maybe your intestines have a hole in them? Maybe is there something problem where things are getting stuck somewhere? Can they get a better idea of what's inside of you rather than doing an endoscopy? So it's just another method for looking at the body and getting a better idea of what's going on inside of you. All right. So this has been the kind of the background information of radiation, just because I thought it'd be good to have a video on all this for anyone that's interested, just to better try to educate all of you into the whole entire promise. Okay. Well, thank you so much for listening, and I hope that I hope you learned something new from this video. And if you have any questions, please feel free to ask. You can always message me, or comment below in the comments, message me, email me, whatever it is that you need for help. Okay. And if this is your first time here, if you haven't yet before, hit that like and subscribe button. And thank you so much for watching. I really appreciate you, and I look forward to seeing you next time. Bye now.